Now, our textbook actually start by developing Taylor series, and then from there go to special case, which is the Maclaurin series. Now, with me, I will start with Maclaurin series, and then go to generalization in Taylor series. Okay. Now, we start with a function. Suppose that a function fx, let me use the word suppose here. Suppose a function fx can be represented by a power series. Can be represented by a power series. Now, the procedure that we use here to find the Maclaurin series will be as the following. Suppose I have this power series, okay, with coefficient Cn. So when I expand it, fx equals to c0 x to the 0, c1x, c2x squared, c3x cubed, and so on and so forth. Okay, suppose that's the power function extension. Now then, to find c0, I substitute the x by 0. Now all of a sudden, all the terms with x will cancel, and I have only c0. Okay, now that's our first step. Step 2, step 1, I do the first derivative. When I do the first derivative, c0 cancels. I get c1 plus 2c2x plus 3c3x squared. Let me go on. 4c4x cubed plus 5c5x to the 4th and on. And to find c1, like before, I set the x equals to 0. So f prime 0 equals to c1. I go to the next step. I do another derivative. We try to find patterns here. So I keep on doing derivative to find pattern on Cn. Okay, but from here, if I do derivative, I'll get 2c2 plus 3 times 2c3x plus 4 times 3c4x squared plus 5 times 4c5x cubed and on. Then when I set f double prime x equals to 0, then I will get 2c2, which implies c2 equals to f double prime 0 over 2. Now notice that this is a power series centered at 0. This is Maclaurin series. That's a power series at x equals to 0, such that the x, therefore, gets substituted by 0. Let me do 2 more steps, just to get the pattern. Okay, so step 3. I do another derivative, f triple prime x equals to 3 times 2c3 plus 4 times 3 times 2c4x plus 5 times 4 times 3c5x squared and on. Set x equals to 0. F triple prime 0 is 3 times 2c3. Therefore, C3 equals to F triple prime 0 over 3 times 2. Step 4. So I keep on doing this because I want to see pattern. When I do the fourth derivative, I will get 4 times 3 times 2c4 plus 5 times 4 times 3 times 2c5x, so on and so forth, setting x equals to 0. So the fourth derivative at 0 equals to 4 times 3 times 2c4. So the coefficient for x to the fourth is the fourth derivative of the function divided by 4 times 3 times 2. Which, if you think about it, we can actually write it this way. This is 4f to the power to the fourth derivative at 0 over 4 factorial. This one here for C3 is the third derivative of the function at 0 over 3 factorial. C2 can be written as the second derivative of the function at 0 over 2 factorial. C1 is the first derivative of C at 0 over 1 factorial. And C0 is basically the function at 0 divided by 0 factorial, which is 1. So now, in general, remember we say that fx equals to the summation for n from 0 to infinity of Cn x to the n, right? Now, we already have the coding, the formula for the coefficients, which is the nth derivative of the function at 0 over n factorial times x to the n. Okay, now we call this Maclaurin extension of the function. That's Maclaurin series. Okay, you will see Maclaurin series is a power series. That's a power series about x equals to 0, centered at origin. Now, Taylor series is power series about x not equals to 0. Now, if we have power series about x equals to a, so you recenter it, we call that Taylor series. And the Taylor series is given by the summation n equals to 0 to infinity of the nth derivative of f at a, not at 0 anymore, over n factorial times x minus a to the n. So you basically recenter it. We basically recenter it. Now we use Taylor series, especially if you try to have the power series converges to the function faster. Now, from here, I will develop two very important Taylor series to the point that you should memorize it, but because your test is open book anyway, so at least you need to know where to find it, okay? A very well-known one, very well-known, very well known. Mclaren series. The first one is y equals to, or let me use fx, is fx equals to e to the x, that is then represented by the summation from 0 to infinity of x to the n over n factorial. To the point you should memorize this. Okay, to the point that you should memorize this. Okay, let's see how it is being done. Proof. Fx equals to e to the x. Now what is f0? F0 is e to the 0, that is 1. Right? So you see that your C0 is 1 over 0 factorial. That's 1. Now when I do the derivative, I still get e to the x. So f prime 0, that's still 1. And C1 will be 1 over 1 factorial, that's still 1. Okay. F double prime x, that's still e to the x. F double prime at 0, that is still 1. So C2 is that 1 over 2 factorial. So you see that every time I do the derivative, any derivative of e to the x is e to the x itself. And the nth derivative of the function at 0 will be 1, such that Cn will be that 1 over n factorial. So the function fx, the Maclaurin series centered, of course it's centered at 0, will then be Cn, which is 1 over n factorial, times x to the n, which is x to the n over n factorial. Which, if we expand, if you try to write it out, that will be when n equals to 0, that's 1, and then x over 1 factorial, that's just x, right? And then plus x squared over 2 factorial plus x cubed over 3 factorial, so on and so forth. Now, so far we still have the assumption that this is the power series expansion. Later on, we need to confirm one thing about the radius of convergence. If the series actually convergent to the function, okay? If the series actually converges to the function, that's one very important one. The second one is, the important one is fx equals to sine x. It will be represented by the series n equals to 0 to infinity. I believe that's alternating -1 to the n. And then it's an odd function, so x to the 2n plus 1 over 2n plus 1 factorial. proof. Fx equals to sine x, f0 equals to sine 0, that's 0, such that c0 is just 0. The first derivative, that's cosine x. F prime 0 will be cosine 0, which is 1. So C1 is 1 over 1 factorial. Double prime x, that will be negative sine x. Double prime 0, that will be 0. So C2 equals to 0. Now, so you start noticing that when the n is even, the coefficient is 0. Okay? And when the n is odd, then it depends if the n is how to say that? It's 1, 3, 5. It's a modulus 4 plus 1 or modulus 4 minus 1. How to say that? So C1 is modulus 4 plus 1. C3 is modulus 4 minus 1. So this will be negative 1 over 3 factorial. As you can expect, and later on you will get C5. C4 will be 0, right? C5 will be positive. C7 will be negative. You see that? Okay, now the thing is, can you build this? Can you build this series? C1, C3, C5, C7, and on, having the following pattern: 1 over 1 factorial, negative 1 over 3 factorial, 1 over 5 factorial, negative 1 over 7 factorial, and on. Can you find the pattern? Notice that the n here increased by 2, starting from 1, right? Okay, so later on in general, that will be, on the denominator, that will be 2n plus 1 factorial. Is it right? Starting from n equals to 0. On the top is always 1, except the sign depends on the n, that will be negative 1 to the power of n. So when n equals to 0, that's positive. When n equals to 1, that's negative. When n equals to 2, that's positive, and on. So the function fx equals to sine x now can be represented by the series from 0 to infinity of negative 1 to the n over 2n plus 1 factorial times x to the n. Now, our textbook then moved the denominator, to be under x. Basically trying to show you that this is an alternating series, right? And we get x to the n over 2n plus 1 order. Okay. So try to memorize this also. Let me just blue color. Now the consequence for this is the series for cosine. But fx equals to cosine x, that's simply the derivative of the series for sine, equals to the derivative respect to x of sine x. Therefore, that is the derivative respect to x of the series. I'm sorry, this should be to the 2n. I missed something here. It should be to the power of 2n plus 1. 2n plus 1. Because the c is, this is for cn, right? This is for cn. I'm sorry, c2n plus 1. Okay. So it should be 2n plus 1 here. I almost get it wrong. Now then, I do the derivative of that to get the series for cosine. This is x to the 2n plus 1 over 2n plus 1 factorial. That is the same to the summation from 0 to infinity, -1 to the n, and then 2n plus 1 factorial at the bottom, and we do the derivative respect to x of that x to the power of 2n plus 1. Now notice that I will then have coefficient 2n plus 1 moving forward. Over 2n plus 1 factorial. Now then the 2n plus 1 cancels. I now have this series, x to the 2n over 2n factorial. And it makes sense because if you think about it, a long time ago we know that sine is an odd function. Notice that we can represent that by a polynomial with odd degrees. And cosine is an even function. We can represent that as with polynomial with even degrees. Okay. Now, using these three, suppose, for example, let me see if I have problems in the textbook that I can use. For example, number 30. Number 30, the question is, use that series to find Taylor Maclaurin expansion for fx equals to cosine pi x over 2. Now notice that I basically convert or change the x becomes pi x over 2. So this is equal to the series from 0 to infinity of -1 to the n pi x over 2 to the 2n over 2n factorial. Notice how I substitute that, right? And of course, we can simplify that to be the series from 0 to 1 to 0 to infinity of the alternating series. I get pi to the power of 2n, x to the power of 2n over 4 to the power of n times 2n factorial. Does it make sense? By the way, just for fun, extra problem from me, can you find the 20th derivative of this function at 0? The way we do it, you will see then what is the n? If the 20th derivative, right, at 0, it implies the n equals to what? You need to get C20, right? You need to get C20. Hold on. Is it to 20 factorial? We don't know yet. I don't know yet. But let's see. So n equals to 10. Why? Because how to say? We have the following. We will be looking at f the 20th at 0 over 20 factorial, right? Okay. Of x to the 20. Now, but if you compare that with that, you will see that it will match when n equals to 10. So you will get f 20th derivative at 0 over 20 factorial is equal to pi to the 20th over 4 to the 10th 20 factorial. Of course, 20 factorial cancels. So the 20th derivative at 0 of that function is equals to pi to the 20 over 4 to the 10th. Let's do more. How about number 34? Let me do it here. Number 34, find Maclaurin series for fx equals to x squared, natural log of 1 plus x cubed. Let's start with natural log of 1 plus x. I wonder if you remember that. That's the integral of 1 over 1 plus x dx. Do you remember that? Right? Now, of course, it would be nice if you memorize that. Right? course, you can just cheat from the book. But then you will see this is n0, that's -1 to the n, x to the n plus 1 over n plus 1. Or I can change the counter. Instead of starting from 0, I now start from 1. So -1 to the n minus 1, x to the n over n. Now, therefore, we can get natural log of 1 plus x cubed. What I want to say is this. If you happen to memorize the expansion for this, you get that right away. You don't need to show this part. Okay, you don't need to show that part. I show it there just to show you how the textbook actually get it. Now then, what we do next is we substitute the x here by x cubed. So I will get the summation from 0 to infinity of -1 to the n minus 1 x cubed to the n over n, which is the series from 0 to infinity of -1 to n minus 1 x to the 3n over n. Now then, multiplying by x squared outside of that, I multiply by x squared to that series. Why does it go back to starting from? Oh, you're right. Start from 1. Thank you. Start from 1. I get so used to it. Start from 1. And it won't be start from 0 because if n equals to 0, this becomes undefined, right? Okay, so thank you. I multiply that x squared in, so it's 1 here. I'll multiply the x squared in, so I get this series. Okay, now suppose this is our function, then f x equals to x squared natural log of 1 plus x cubed. Then can we find the 20th derivative of the function at 0? Then you look at the series. You look at the series. The terms actually this. That's the term, right? That's the term. Set this equals to c 20th x to the 20th. When you match the x, what will the n be? And n equals to 6, right? N equals to 6. Now then, we know that c 20th equals to -1 to the 6 minus 1 over 6. That is equal to the 20th derivative at 0 over 1 factorial. Okay, so then we can say that the 20th derivative at 0 is equals to that's negative 1/6 times 20 factorial. I don't think you want to do the derivative one by one like 20 times, right? No, you don't want to. Please don't do that. But you see the technique that I show you here can do that derivative actually a lot faster by looking at the Maclaurin series. By looking at the Maclaurin series, and then you re-engineer that back because we know the coefficients. We know the coefficients for this Maclaurin series. Okay, we know the coefficient for that Maclaurin series. Okay. Now let's go to Taylor series. Suppose, let me pick up the question. Suppose we have, what is good? We want to create a Taylor series number 18. Number 18. Find Taylor series for fx equals to sine x at a equals to pi over 2. So the center is not at 0. The center is at pi over 2. Solution fx equals to sine x. So f pi over 2 instead of 0, pi over 2, sine pi over 2 is 1. F prime x is cosine x. F prime pi over 2 equals cosine pi over 2 is 0. F double prime x will be negative sine x. F double prime at pi over 2 equals to negative cos, and actually negative sine of pi over 2, that's negative 1. I think we end up with pattern, huh? We end up with pattern. And the pattern is C0 will be 1 over 0 factorial. C2 will be negative 1 over 2 factorial. C4 will be 1 over 4 factorial. C6 is negative 1 over 6 factorial. Now, I wonder if you see pattern here. Cn will be actually C2n. I'll call that Cn. C2n. Yeah, I call it C2n. I need to do some correction up there. Somewhere. Yeah, C2n. C2n N is 0, that's positive. When n is 1, that's negative. So it will be negative 1 to the n, okay, over 2n factorial, just like that. Therefore, fx is equal to the series from n equals 0 to infinity, negative 1 to the n over 2n factorial times x minus pi over 2 to the power of 2n. Okay. Number 44. It gets a lot more fun. From here, it gets a lot more fun. For example, calculate 1 over the 10th root of e correct to 5 decimal places. We know that e to the x is x to the n over n factorial, right? So what happens if I have 1 over the 10th root of e? That's basically e to the negative 1 over 10. Is it right? Now I will substitute that x by negative 1/10. Which is the series and equals to 0 to infinity. Notice that it becomes alternating series, right? Over n factorial 10 to the n. Right? We learn from alternating series that we learn from the alternating series. This is alternating series. We learn from alternating series that the error will be less than the next term. Right? The error will be less than the next term. Actually, that's not how I want to do it. That's not what it is. The next term has error. How to say that? Yeah, the error will be what is the best way to? Yeah, what I wrote earlier is correct. This one. Now then I will set this to be less than 5 decimal places, 0.00001. absolute here. So 1 over n factorial 10 to the n is less than 1 over 100,000. I need to find n first. We need to find n first. How many terms do I need to add to get to that accuracy? Okay, so basically 100,000 should be less than n factorial 10 to the n. I think 4 is good, right? And n equals to 4. I'm sorry. I made a big mistake here. This is actually n plus 1 factorial 10 to the n plus 1. So actually n equals to 3 is good enough, right? When n equals to 3, notice that there will be 4 factorial times 10 to the 4th, right? 4 factorial is 24 times 10 to the 4 is 10,000, which will give us 240,000. So I only need to add 3 terms. I just need to add 3 terms. So just need, I should not use the word just. So need 3 terms. 3 non-zero terms to be more precise. Okay, so e to the negative 1 over 10, which is 1 over 10 root of e, can be approximated from n equals to 0 and then when n equals to 1, when n equals to 2, up to n equals to 3. I should not say need n terms. I think I should say up to not 3 terms. It's not correct to say up to n equals to 3. That's what I meant. 3 factorial 10. Okay, so this is 1 minus 1 over 10 plus 1 over 200. Actually, that's minus 1 over 3,000. Okay, let me use my calculator to compute that. 1 minus 0.1 plus 1 over 200 minus 1 over 3,000. That gives me 0.9046666 on, while e to the negative 1/10 itself, if I use calculator, give me 0.904837 blah blah blah. No, this is not. I think I do some miscomputation here.
3 factorial is 6.
Thank you. So it should be 6,000 here. I need it. So 1 minus 0.1 plus 1 over 200 minus 1 over 6,000. Thank you. I really need it. 8, 3, 3, 3. Okay, so if you compare it next to each other, so you see they start to differ at the 6th decimal place, right? Next one. Another one that is important, binomial expansion. Binomial expansion. We have known from precalculus that 1 plus x to the power of k is equal to the series from 0 to k of k, actually not kn. No, that's right, that's k then. Okay, my bad. From k, choose n x to the n. So basically when n equals to 0, that will be k choose 0, x to the 0 plus k choose 1, x to the 1 plus k choose 2, x squared, all the way to k choose k, x to the k. That's what we know. Now the thing is, it turns out this pattern can be used even when k is not an integer. Okay, notice that k choose n means k factorial over n factorial, k minus n factorial. Is k over n a fraction? No, it's not. It's not. Not k over n. This is k choose n. This is a combination notation. On your calculator, this will be k combination n on your calculator. Let's do an example. One that we already know. For example, 1 plus x to the power of 5. Okay, according to Pascal triangle, it's 1, 5, 10, 10, 5, 1. So this will be 1 plus 5 x plus 10x squared plus 10x cubed plus 5x to the 4th plus x to the 5th. That's the extension. Now let's pick, for example, this 10 here. How do we get this 10? How do we get this 10? That 10 comes from 5 combination 2, which means 5 times 4, we have two terms up there. The two terms comes from that 2 underneath. I think I should say 2 factors. Over 2 factorial. Now, let's change that 5, the exponent, to be, let's say, 1/2. So 1 plus x to the power of 1/2, that will be equals to the series from 0 to infinity. The k now becomes 1/2. Choose n x to the n. Okay, so when n equals to 0, that's 1/2 choose 0, x to the 0. But 1/2 choose 0 is basically 1. Okay, plus 1/2 choose 1, x to the 1. Oops. Plus 1/2 choose 2, x squared, plus 1/2 choose 3, x cubed, and on. Now I can go forever, right? Because this series goes forever. Now, what is 1/2 choose 0? 1/2 choose 0 is 1. Now, 1/2 choose 1 means 1/2 on the top, only one factor, over 1 factorial at the bottom. 1/2 choose 2 means you have 2 factors on the top, start from 1/2, and then 1/2 minus 1 over 2 factorial. 1/2 choose 3 means start from 1/2, 1/2 minus 1, 1/2 minus 2 over 3 factorial, and on. Okay, so this is equal to 1 plus x over 2 minus, what's that? X squared over 8, and then plus x cubed over, give a second, 1/4, 16, minus so on and so forth. That will be the series. Now I will use this to help me working on number 46. Part A, expand 1 over 4th root of 1 plus x as a power series. Solution. You can see that 1 over 4th root of 1 plus x as 1 plus x to the power of negative 1/4. Right? And this is equals to the series from 0 to infinity. The k is negative 1/4. Choose n x to the n. We may not get some nice pattern, but you also realize that we just need the first couple terms. Actually, I'm done with this. I'm done with part A. Part B. Estimate one over fourth root of 1.1 to 3 decimal places. So 1 over square root of a fourth root of 1.1 is equals to 1 over fourth root of 1 plus 0.1. In other words, I replace that x by 0.1. Right? And you need 3 decimal places. You look at this, you can just tell right away that when n equals to 4, actually n equals to 3 will be good. Right? For n equals to 3, you have negative 1, 4, choose 3, 0.1 to the n, to the third. Now this guy is already something small, 0.001. Right? Okay, so I just need to go up to n equals to 2. Let's confirm. What is this negative 1, 4, choose 3? Negative 1, 4, choose 3 means we have 3 factorial at the bottom. On the top, I should have 3 factors too. Okay, so that's for this part. Maybe I write it here. That's negative 1, 4, choose 3. That's what it means, which is negative 1, 4 times negative 5, 4 times negative 9, 4 over 3 to 1. That's negative 45 over 6 times 64 times 0.001. So you see that the magnitude is already less than 3 decimal places, right? So I need to add up to n equals to 2. Okay, so that 1 over fourth root of 1.1 can now be approximated by negative 1, 4, choose 0, 0.1 to the 0, plus negative 1, 4, choose 1, 0.1 to the 1, negative 1, 4, choose 2, 0.1 straight. That's equals to 1 plus negative 1/4 over 1, 0.1 to the 1, plus negative 1/4, negative 5/4 over 2 factorial, 0.01. This is 1 minus 0.1 over 4 plus 5 times 0.01 over 32. Let's see, what's that? 1 minus 0.1 over 4 plus 0.05 over 32. I get 0.97656 blah blah blah. Now using calculator, the actual value of that 1.1 to the power of negative 1/4. The actual value here is 0.97645 4 blah blah blah. So notice that we are accurate to third decimal place. Oh, by the way, one of when I did my national entrance exam in Indonesia for university, public university, we need to take a national test. It's not like in America, you just take SAT. Right there, we have certain kind of SAT, but trust me, it's a lot more difficult than the SAT we have here. One of the question is without calculator, estimate sine 1 to 5 decimal places without calculator. Actually, to be more precise, actually not sine 1, but sine 1 degree. Correct to 5 decimal places. And the key is really knowing the expansion of sine. Sine x equals to the series from 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Are you with me? Now the thing is, this x here is in radian, this is in degree. So how to change that 1 degree into radian? One degree is equal to 1 degree times pi over 180 degrees. Now then, sine 1 degree is equal to sine pi over 180. So this is equal to the series negative 1 to the n pi over 180 to the power of 2n plus 1 over 2n plus 1 over. Now you see that this is alternating series. This is alternating series, and actually when n equals to 2, it's even when n equals to 1, I think it's big enough. Like pi over 180 is approximately, this is 3 over, that's 1 over 60. Right? If you want to have the, so you see this is approximately, I need to find the n, right? So to what power, look at this. What is the power here such that this is less than 0.00001? Okay, not to say that I have 2n plus 1 factorial at the bottom. Okay, in other words, if I change it into, this is 1 over 60 to the n times 2n plus 1 factorial should be less than 1 over 100,000. I need to find how many terms first. So 100,000 should be less than 60 to the n 2n plus 1 factorial. Then from there you estimate. I think n equals to 3 is good enough. Get 7 factorial. 6 times 6, 36. 36 times 6, 216 with 3 zeros. That's way too big already. 7 factorial. I think 2 is good enough. And n equals to 2, maybe not, huh? So I get 60 squared times 5 factorial, 3,600 times 5 times 4 times 3 times 2, 120. So what is this? 144 times 3 is 300, 433. Oh yeah, when n equals to 2 is good enough, huh? So to do that estimation, I just need, when n equals to 0, pi over 180, when n equals to 0, and then when n equals to 1, and when n equals to 2. I will estimate this using 1 over 60 plus 1 over 60 cube times 3 factorial. Actually, what am I doing? That's not true here. That's not true. So I don't need to go that far. I'm good enough here. I need to fix something. This should be 2n plus 1. So n equals 1 is good enough. Yeah, actually n equals to 1. N equals 1 is good enough. This is incorrect. I just need 2 terms there. 0th and first term. My bad. So when n equals to 1, I get 60 cubed times 3 factorial, that's 216 with 3 zeros. Yeah, n equals to 1 is good enough. So I will use this approximation. 1 over 60 minus 1 over 216 with 3 zeros times 3. Now let's see if I'm right. Sine 1 degree equals to what? So sine 1 degree is, according to my calculator, 0.0174524. Now, if I use this estimation, 1 over 60 minus 1 over 60 cubed times 6, not 3. I get 0.016665. So you see that I'm off pretty big, huh? But that's because I estimate my pi using pi over 180 by 1 over 60. So if you want to take care of that possible error, then you do another one. Okay? That's how I do it. That's how I did it in that test. So it's kind of painful to compute this by hand, though. Very painful, to be honest with you. But then I remember I get that work done. I will stop here for now. I will give myself a break. I come back later on in approximately 10 minutes. I come back at 8:50. Oh, I see a message coming in. How long did I have on the test? We have 3 hours, but that's a lot of problems there. That's a lot of problems. So you need to do things like by a very close estimate really fast. And it's without calculator. The calculator we have, we actually use calculator, but the calculator is only the very basic one. Add, subtract, multiply, divide, square root, natural log, log. But no sine, no cosine. It's a cheap calculator. It's if you know the type of calculator we use. No. I'm sorry. We don't have natural log. We don't have log. Yeah. So the closest one we get is actually the square root. The $5 calculator, we have add, subtract, multiply, divide, square root. Yeah, that's all we have. Of course, if you ask me how will I actually do this, how did I do this test at the time? Okay, how I did that is this way. I get this first. Okay, and then I start computing it right away. I compute this and then this. When I compute this part, I see what kind of error do I have, how small it is. If it is too small, less than 0.0, less than 5 decimal places, I don't add them anymore. You see? Does it make sense for you? What I did here, I look for how many terms, right? But eventually you need to add, you just need to keep on adding the terms. And how do you know when to stop? When the terms you are adding already is less than 5 decimal places. Right? Yeah, that's how it is being done. You need to add the terms anyway. So it seems like, oh, Thomas, it takes you so much so long to do it. Nah, that's because I need to explain to you. Right? That's because I need to explain to you. But otherwise, it's just like that. It's just like that. Okay. Let's take a break. In 10 minutes, we come back. We will go on to the next page of the exercise set. Give me a second. The exercise, the next page, we take a look on page 790. What we do in this page, basically, just application of the series. For example, number 48. The question is, evaluate the indefinite integral as infinite series. So integral of e to the x minus 1 over x dx. the way we do it, we see e to the x first as the series of 1 over n factorial from n equals to 0 to infinity, right? So if we have e to the x minus 1, that will be, oops, I'm sorry, I should have x on the top, x to the n on the top, x to the n on the top. Now that is actually 1 plus x squared over 2 factorial and on, right? Basically, when I subtract by 1, I will start from the first term. Is it right? Does it make sense? Now then, when I divide by x, then that will be the exponent, oops, the exponent will be subtracted by 1. Now, integrate them. That will be integral of the series from 1 to infinity x to the n minus 1 over n factorial dx. But that is equals to the series from 1 to infinity of the integral. That is the series of x to the n over n times n factorial. Don't forget, plus constant. Okay. Number 52. Do it here, 52. Integral from 0 to 1 of sine x to the 4th dx. And we want to be accurate to 4 decimal places. Now I will show you how I will do it without finding the number of terms. So this is equal to integral from 0 to 1, the series from 0 to infinity, negative 1 to the n, x to the 4th, 2n plus 1 over 2n plus 1 factorial dx. Is it right? This is the series from 0 to infinity. Let me bring the alternator also out. Over 2n plus 1 factorial integral from 0 to 1 x to the 8n plus 4 dx. That will give us x to the 8n plus 5 over 8n plus 5 from 0 to 1. But when x equals to 0, that's 0. When x equals to 1, we get something else. We got 1. So this is negative 1 to the n over 8n plus 5 times 2n plus 1 factorial. I need accurate to 4 decimal places. So I will just keep on adding it, okay? When n equals to 0, that will be 1/5, right? When n equals to 0. When n equals to 1, that's minus 1 over 13 times 3 factorial. Plus when n equals to 2, 21 times 5 factorial. 1 over when n equals to 3, 24, 29, 7 factorial. But let's see. 29 times 7 factorial is what? Yeah, 29 times 7 factorial. 29 times 7 factorial is already 146160. So it's more than 10,000 already, right? So I don't need to go that far. I just need the first 3 terms. 1/5 minus 1 over 13 times 6, 7, 8, plus 1 over 21 times 120, 2, 5, 2, 0. I get 0.187576. To 4 decimal place. So if I round it to 4 decimal places, this is 0.1876. Okay, so you see that I didn't really look for how many terms I need. I just keep on adding until the next term is less than the error that we want. Would you like to do number 54? I do it. Number 54. So integral from 0 to 0.5, which is 1/2 of x squared e to the negative x squared dx. And the error will be less than 4 decimal place. Solution. E to the x is the series from 0 to infinity of x to the n over n factorial. So if I change that x becomes negative x squared, so this becomes negative x squared to the n, which becomes negative 1 to the n. That's alternating. Okay, x to the 2n over n factorial. Multiplied by x squared. And I basically add the exponent by 2. Right? Then the integral from 0 to 0.5 x squared e to the negative x squared dx will be the integral from 0 to 0.5 of that series. That is the series from 0 to infinity y n. And then I get x to the 2n plus 3 over 2n plus 3 n factorial from 0 to 0.5. Now I get 0.5 is 1/2, right? So let me write it this way. This is times 1 over 2 to the power of 2n plus 3, 2n plus 3, and factorial. What do you think? Okay, and I will keep on adding until the next term is less than 4 decimal places. Less than 0.0001. So when n equals to 0, that's 1 over n equals to 0, 1 over 8 times 3 minus when n equals to 1, 2 to the 5th, that's 32 times 5 plus when n equals to 2, 2 to the 7, 128 times 14, 17, 0, 1, 2, not 17, that should be 7. And then the next one will be 1 over 256, 512 times 9 times 6. But I think that's already less than 5 decimal place. What's that? What do you send everyone, Andre? For these questions, do we just estimate? I need to see what it looks like. Let me see. Oh, that one is something later. Number 4 in the test. That's later. Don't worry about it. Not now. Not now. That's later. No, and in fact, we don't estimate. That one you have to get the exact value. Let me see. 512 times 9 times 6. This guy is already, the last term here, already less than 0.0001, which is 1 over 10,000. The magnitude is already less than that. So I would just add up to 3 terms. Okay, so that's 1 over 24 minus 100, 1 over 160 plus 1 over 1792. Get 0.03597. the one you asked me, that will be the last part of today's lesson, basically the last part of this semester's lesson. But let me slowly go to, for example, number 56. How to do number 56? Find the limit. Limit x going to 0 of 1 minus cosine x over 1 plus x minus e to the x. I think you can use L'Hopital rule for this, right? Okay, but they say use series instead. Okay, we use series. So limit x going to 0 of cosine. There will be 1 plus x squared. Actually, no, minus. One minus x squared over 2 factorial plus to the 4 over 4 factorial and on over 1 plus x minus, this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and on. Cancel this, cancel that. We get limit x going to 0 of, on the top I will get x squared over 2 factorial plus x to the, I'm sorry, minus, not plus, x to the 4 over 4 factorial plus x to the 6 over 6 factorial divided by negative of x squared over 2 factorial plus x cubed over 3 factorial and on. Now, how do you take it from here? Divide by x squared on the top and the bottom. Right? That's the technique we learned before. So this is negative limit x going to 0 of 1 over 2 minus x squared over 4 factorial plus x to the 6 over 6 factorial and on. Big over 1 over 2 plus x over 3 factorial plus 4 x squared over 4 factorial and on. But then when x equals to 0, you just get 1. We can try using L'Hopital rule. I think we need to do it twice, huh? This is sine x over 1 minus e to the x, L'Hopital again. It will be cosine x over negative e to the x, which is 1 over negative 1, right? So we get the same result. Number 60. If you have a chance, take a look on how you compute. It's in the book. The series for tangent x, which is sine x over cosine x, right? Now, can you find the quotient? This is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and on. divided by 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial and on. And I usually ask you to get the first 3 or 4 terms only, non-zero, the first 3 or 4 non-zero terms. Now, I would like to show you how to apply that idea to number 62, for example. Y equals to, I have a chat coming in. What did you cancel from the first step to the second step? Which one you were referring to? I'm sorry, I didn't see. I think you were referring to number 56, huh? So when I cancel 1 with negative 1, I get the opposite of this. And then I cancel x and 1, I get the opposite of this. I hope that's your question. I didn't see your notes earlier. Okay. The algebra. Yeah, that's the algebra. Number 62. E to the x natural log of 1 plus natural log of 1 plus x. Now e to the x is the series. Let me do it this way: 1 plus x squared over 2 plus x cubed over 6 x to the 4th over 24 and on. That's for e to the x times natural log of 1 plus x. I wonder what's that. I don't remember. Then I cheat from the book. Do you know where to find it? X minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 and on. Now then I will start multiplying. Now notice that the lowest degree must be degree of x, degree of 1 must be coming from this guy and this guy. Right? Okay, so the first term will be just x. How about x squared? X squared must be coming from this pair and this pair. Are you with me? What will that be? The first product is negative 1/2 x squared. The second product is plus x squared. So that's right. That will be plus 1/2 x squared, right? Now let's see. How about x cubed? How to get x cubed? X cubed must be this pair and this pair and this pair, right? So that's 1/3 minus 1/2 plus 1/2. Oh, okay, so that's equals to 1/3 x cubed. You know what? Let's try more. I wonder if we can get a pattern. What happened to x to the 4th? X to the 4th will be negative 1/4 plus 1/3 minus 1/4 plus 1/6, right? Okay, let's see. So negative 1/4 plus 1/3 minus 1/4 plus 1/6. That's -2/4 plus 3/6. That's 0. Oh, so that will be 0. Let me write it down. So that will be 0x to the 4th. Usually we don't write that term down there. Okay. That's for number 62. I was expecting that to be 1/4x to the 4th, to be honest with you. But nah, there's no such nice thing. Let's do something a bit messy. Number 61. Number 61. I have number 60 in mind, but that's no fun. Let's do number 61. Y equals to x over sine x, which is x over x minus x cubed over 3 factorial plus x to the 5th over 5 factorial and on. Now I need to do long division. X divided by x minus x cubed over 6 plus x to the 5th over 5 factorial, 6 times 120. That's one time. Right? And then for the second term, anybody can help me? Plus x squared over 6. Is it okay? Negative 1 point over 120 plus 1 over 6. Multiply by 10, multiply by 3. So that will be 7 over 3, 60. Okay. So positive 7 over 360 x to the 5th. So it will be plus 7 over 360 x to the 4th. I just need the first 3 non-zero terms. So I will get this is 1 plus x squared over 6 plus 7 over 360 x to the 4th. As we expect, it's supposed to be an even function. Why? X is odd, sine x is odd. Odd function divided by odd function is even function. Okay. Now let's see number 64. I will think I will do 3 more problems from here. Number 64. The series from 0 to infinity of -1 to the n pi to the 2n over 6 to the 2n factorial. Now you massage that until it looks like one of the special series. -1 to the n, and this is pi over 6 to the 2n over 2n factorial. If I change this to x, what will that be? That's cosine x, right? Number 66. Three to the n over 5 to the n factorial. I will rewrite this as 3/5 to the n over n factorial. Is it right? But this is e to the x. This is e to the 3/5. Number 68. 1 minus natural log of 2 plus natural log of 2 squared over 2 factorial minus natural log of 2 cube over 3 factorial and on. This is an alternating series. -1 to the n, right? And I have ln2 to the power of n over n factorial. Agree? Is it okay so far? Now you massage this. This is equal to the series negative natural log of 2 to the power of n over n factorial. Okay, but if this is by x, it follows e to the x. Right? Okay, now let me get the question that you asked me earlier. Give me a sec. Which one is that? Mhm. Oh, why I cannot open? Okay. Why I cannot open? Now I can. So let me get this one. Yeah, you need to be good in massaging. Oh, this is from n equals to 1, huh? So the series from 1 to infinity, -1 to the n plus 1. This is 3 to the n over 4 to the n with extra 4 at the bottom. So this is equals to, I take the 1/4 out, okay? I take the 1/4 out, and actually let me take the negative 1/4 out. So I end up with negative 1 to the n, 3 to the n, over 4 to the n. Everybody happy, that's to the n. But notice that this is geometric series, right? This is negative 1/4. The first term is negative 3/4. The ratio is negative 3/4. Right? Okay, so let me multiply the top and the bottom by 4 here, by 4 here, so I get negative 1/4 times negative 3 over 4 plus 3. Am I making a mistake? Or what we learned previously? Yeah, basically things put together now. Basically things put together right now. So we will get positive 3 over 28. Let's see the next one. I think I actually wrote some hard question somewhere here. I think part B, and yeah, part B I think is quite hard. We start from 1. And the end there actually quite troublesome. This is the series n 3 to the n 4 4 to the n. I take the 1/4 out. This is n times 3/4 to the n. Now this mimic, so this part, the summation part, mimics the summation part mimics nx to the n. How do you play it? Let's take this one, the series from 0 to infinity of x to the n. That's 1 over 1 minus x, is right? Now the derivative, so we start from 1 now, will be nx to the n minus 1. But the derivative of this will be 1 over 1 minus x squared, is that right? So I will multiply x in Is it okay? That's what it is. Now then, this is equals to 1/4. You replace the x by 3/4. Okay, so that's 3/4 over 1 minus 3/4 squared. Okay, 1/4 times 3/4 over 1 over 16. That's equals to 3. Nice number. We have more questions? Is that all? Last one. That one. Hold on. I see a message coming in. Isn't the derivative has a negative because of chain rule? But you also have negative from the negative x. No? Right? So yeah, that gives me 1 over 1 minus x being squared. The last question here is basically, what do you think you will do here? Partial fraction decomposition. Okay, and don't worry about that 3. You can actually deal with that 3 quite easily. I think you will get 3 over 2 here and then negative 3 over 2 here. Is that right? Will that make it? Yeah, but then that's basically the same to I factor 3 over 2 out. And I get 1 over n minus 1 over n plus 2. Then I do telescoping. That's 1 over 1 minus 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over 3 minus 1 over 5. And keep on going until I get the limit and goes to infinity of, let me, actually, I need to be careful here. Hold on. Let me do more things. I know some of them don't cancel that well. Give me a second. So I know this 1/3 cancels here, 1/4 cancels here, 1/5 later on cancels. So I have 1 plus 1/2 not cancelled, but then later on I have minus 1 over 1, 2, so n minus 2 minus 1 over plus 2 plus when I go to 4 times. 1 and 2. This is 1 and this is 2. I need to put limit there. Sorry. But that's basically 0. Sum is 1 over 4. Okay, very last question. I feel like I don't really want to leave you. Number 70. 1 over 1 times 2 minus 1 over 3 times 2 cubed. Ooh. Plus 1 over 5 times 2 to the 5th. So this is the summation. And equals to 0 to infinity 135. So there will be 2n plus 1, right? And 2 to the 2n plus 1. Oh, alternating. Ta-da! Can you tell what is the sum? Let's do some massage. The thing is, all of them has factorial at the bottom though. Which one doesn't have factorial? Tangent inverse x. Let's see, tangent inverse x has this pattern. -1 to the n, x to the 2n plus 1 over 2n plus 1. Hey, you know what? This is what I want, right? I have -1 to the n. I have the denominator 2n plus 1, and I can change my x to be 1 over 2 to the power of 2n plus 1 on the top. Right? So this is equal to tangent inverse of 1/2. That's it. Okay, so it would be nice if you put a mark, kind of like a, what do you call it, the book marker for page 786. That's the table that you need to memorize. You don't need to memorize it, but at least you know where it is and how to use them. Okay. Suggested homework. From this 11.10, number 5 to number 19, and then 29 to number 37, 43, 45, to 69. Okay, to the odd ones. But feel free to skip the questions that you feel like you know what to do. Okay, that's for today. See you then Wednesday.